We're next going to take a more careful look at collisions. One thing we know about collisions is that momentum is always conserved. This is because you have a limited number of objects that are interacting with each other. They are exerting forces on each other, but not experiencing forces from the outer environment. So momentum is always conserved in collisions, which means you can always write down that the sum of the momenta of the objects involved in the collision before is equal to the sum of the momenta after the collision. Kinetic energy, however, is not always conserved, and this is because kinetic energy can turn into other forms of energy during the collision. So we can break down collisions into different types. One type of collision is an elastic collision. This is a collision where both momentum and the kinetic energy of the objects is conserved. In an inelastic collision, only the momentum is conserved. Kinetic energy is not conserved. Then there is a special case of inelastic collisions, which we call perfectly inelastic collisions, and these are where the objects stick together. And in these collisions, once again, momentum is conserved and kinetic energy is not conserved since it is a type of inelastic collision. So looking again at elastic collisions, these are ones where momentum and kinetic energy are both conserved. So the kinetic energy does not turn into some other kind of energy. And elastic collisions tend to be very bouncy since no kinetic energy is being lost. If we think about allowing a ball to have multiple perfectly elastic collisions with the floor, since it loses none of its kinetic energy, it would always rise to the same height after bouncing off the floor. This animation shows a kind of elastic collisions where we have two objects that are of the same mass. Initially, the black box is moving, and it has mass m and some velocity v, and then afterwards the blue box is moving with the same velocity. So you can see in that collision both the momentum m times v and the kinetic energy are conserved since the blue box ends up with all of the black box's kinetic energy. So with this type of collision, we can write down expressions if we need to solve a problem for some unknown. We can write down an expression that conserves the momentum and one that conserves the kinetic energy. Now this second equation, conserving the kinetic energy, this is sometimes a difficult equation to use when solving problems because of all the squares. It makes the algebra tough. So a simpler equation, which we can use if we have the special case where we know we have a perfectly elastic collision and all of the motion is in one dimension, such as the collision that's depicted here, then we can also write down that the difference between the initial velocities is equal to the negative of the difference of the final velocities. So you can use this equation only when it is specified that you have an elastic collision and you know all of the motion happens in one dimension. Otherwise, if you're told that you have a perfectly elastic collision, then you can use the conservation of kinetic energy expression. If you are not told in a problem that you have a perfectly elastic collision, then you cannot use the conservation of kinetic energy expression or this one involving the velocities. If you have an inelastic collision, this is one where only momentum is conserved. And if a problem does not explicitly state that you have a perfectly elastic collision, then you must assume that you have an inelastic collision since they are more common and that you can only conserve momentum. So if a ball were to undergo inelastic collisions with the floor, you would see that each time it would lose some of its kinetic energy upon the bounce and rise up to a lower and lower height. So with an inelastic collision, the kinetic energy is changed into some other form of energy. Maybe the energy goes into crumpling the material of the objects that collide, or maybe some of the energy is lost in the form of heat or sound. A perfectly inelastic collision is a special case of inelastic collision. So once again, only momentum is conserved, But in a perfectly inelastic collision, since we know that the objects stick together and move with the same final velocity, we can use the same symbol to represent the final velocity of both of the objects, since they are traveling together. So now when we conserve momentum, we can replace V1 final and V2 final with just V final, since it's the same for both objects. Then we can factor out that V final and we get a simpler expression because initially we have the two objects, but then we have an object at the end with just one final velocity and a combined mass. So you can see in the animation below that we have a block coming in with some velocity, and now since the final object has twice the mass, in order to conserve momentum, it has half of the velocity. So next we're going to use conservation of momentum to analyze a car accident. And the next video that you will watch is a video showing this accident. Now I want to say ahead of time that nobody is seriously injured, even though the accident looks bad. Nobody is seriously injured in it, but the video is a little bit of lower quality. It's a few years old, and so if you listen very carefully, you can get a lot of information out of the video, but it does jump around and is a little sketchy at times.